So this lesson looks at applications of vectors, and very similar to what you might have already seen in like a physics class or something like that. We won't go as far as you would in physics, but I think it's important that we see some of the applications of vectors. We're going to look at different types of forces. We're going to look at velocity and also tension, which is a type of force. So let's start with this first example. We've got myself and my two kids fighting over a piece of rope, and I just needed an example with three forces here. Mr. Elliott's kids each grab an end of the rope and pull with forces of 250 newtons and 175 newtons at an angle of 45 degrees to each other. And then I'm going to hold the rope in the middle, and I'm going to apply a force as well. And myself, the kids, and the rope all stay stationary. How much force did I apply? What is the magnitude of the force? Now, forces are measured in newtons, which is a kilogram per meter second squared. Don't worry too much about the units right now. When we talk about gravity, that sort of makes a little bit more sense, but just know that forces are in newtons for now. Okay, so to start with, we need to realize that these forces are in equilibrium. That means that they sum to zero, the three forces. If the system was not in equilibrium and there was some sort of resulting non-zero force, then we're going to have an acceleration that occurs in the direction of that result. And that acceleration can be calculated using the newtons, the fact that a newton is a kilogram per meter second squared. A kilogram times meters per second squared. So we know that they balance out, that they sum to zero. I'm applying the exact force I need to counteract the kids' forces. So I've got this drawn out like this. And of course, we were given the two forces, 250 and 175. So we can take a look at labeling those. So if 250 is the bigger force, so that should be down here, and 175, and then an angle of 45 degrees, just like that. There's kind of two ways to handle the fact that you have three forces acting in equilibrium, three forces that are summing to zero. One way to handle it is to imagine that the forces are all head to tail. And if the forces are all head to tail, like this, then they must make a triangle. See how these three forces, if you use the triangle law, add to zero? Force 1 plus force 2 plus force 3 gets you exactly where you started. So that's one way to handle an equilibrium. Okay, that they form a triangle, and you can move remember, you can move vectors around. They don't have any position. I think in this case, though, when the vectors are all tail to tail, it makes more sense to look at my two kids' forces and figure out their sum, okay, and then realize that my force has to be the exact same magnitude and opposite in direction in order to sum to zero. And I think in this case that makes more sense. So what I'm going to do is, because these two forces are tail to tail, I'm going to complete the parallelogram and figure out the sum. And so there you see what I've done. I've just completed the parallelogram. So this is 250, 175. Okay, I've drawn the resulting force from these two forces. If this is 45 degrees, then we know, of course, that this has to be 135 degrees. And we can use the cosine law to figure out the magnitude of the resulting force. So let's just do that. We're going to need a name for that. I'm going to call this just R. It's very common to use R for resultant force. Okay, so using the cosine law, r squared equals 250 squared plus 175 squared minus 2 times 250 times 175 times the cosine of 135. And if you do the work, you should find that the magnitude of that resultant is about 394 newtons. So really, if this R value is 394 newtons, then it must be that I'm pulling also with a 394 Newton force in the opposite direction of R. We could figure out the direction of R if we wanted to, and then you would be able to figure out the angle, because there's a special angle that I must be exerting the force on in order to counteract them. Okay, it's going to be a little bit more in this direction, because obviously the 250 force tends to pull this way. Okay, and there you have it. That's the answer. The answer, if you just need the magnitude of the force I'm pulling with, it is 394 newtons. Now I mentioned we're all kind of pulling on a rope like this. So maybe there's a force there and a force there on the ends of the rope, and then a force that's here. But forces, they don't have position. Vectors don't have positions. You can move forces around so that they're all tail to tail or head to tail or whatever you want. It doesn't matter. Okay, let's try another example. So another common force is what's called tension. So tension is the force exerted by a string or a cable. It's the opposite of compression. So to give you an idea, a really simple example, we've got a student who weighs 70 kilograms hanging from a vertical rope in the gym. Let's assume that they are hanging from their arms, okay? And I'm not trying to be morbid here or anything. So that means that because of gravity, there is a force of gravity applied. Okay, the student, of course, wants to fall. So the force due to gravity this is something you need to know. It's always 9.8 newtons per kilogram. Okay, and there's a little fact if you didn't know that. So this force that's going down, okay, has a magnitude. It's very, very common to call that like F with a little subscript G, force due to gravity. But its magnitude is 9.8 newtons per kilogram times the student's mass of 70 kilograms, which gives you 686 newtons. So that's a 686 Newton force going down towards the center of the earth. Now, if they're hanging from a rope, what is stopping them from accelerating towards the ground? They are in equilibrium. And the reason they're in equilibrium is because of the tension in the rope, which has to counteract the force due to gravity. So the tension in the rope is a force that's operating up, and its magnitude has to be the exact same. So the answer is the tension in the rope is also 686 newtons. Okay. If a heavier student were to do the same thing, then the tension in the rope increases. The tension in the rope if a lighter student were to do the same thing, then the tension in the rope decreases. Eventually, if someone was too heavy, the tension force would be too strong for the rope and the rope would snap. But there's a very simple example of tension. It goes up in this example. Let's look at a more interesting example. So in this example, we're talking about a sign that has a mass of 56.1 kilograms supported by 2 wires attached to a horizontal pole. And we're given the angles of depression on each of the wires. So on the left here, side of your screen, you should see what I call a position diagram. This is what it looks like. You've got this this sign, and I do have a little bit of a force, a vector that I'm showing here. Represents the force due to gravity, and then you have these 2 wires that are holding it in place. So the 2 wires, if you want to think about a vector, they apply a force in this direction and a force in this direction. So like that and like that. Okay, but this is just a picture of what it actually looks like. So I'm actually going to get rid of those for now. Okay, and of course we have the angle of depression on the left is 15 degrees. So we have a 15 degrees here and a 10 degrees here. Okay. Now the sign is 56.1 kilograms. So there's 9.8 newtons per kilogram due to gravity. So we multiply that by 56.1 kilogram. And we get 550 Newton force. Oops. So we know that this force here of gravity has a magnitude of 550 newtons, and it goes down. Okay, now the one thing that's complicated about this is that I like to think of it this way. The position diagram doesn't help us with the forces as much as we'd like. As it turns out, if you have 2 wires that support this sign, the wire on the left, although it's shorter because it makes a bigger angle, it actually takes more of the weight. So this tension in this wire is actually stronger, is more or greater than the tension in the wire on the right. Even though in the picture, this wire is shorter, the actual force here is a vector that's longer. So what we really need to do is take our position diagram and change it into a force diagram. Okay, now these angles do affect the direction of the force. So the fact that this wire makes this angle, or this cable makes this angle, I guess it's a wire, doesn't matter, you know, it does force the force to act in that direction. Okay, and same with this one, it forces it to act in this direction. So what I've redone here is I've drawn this force being larger because I know that it's going to end up bigger. Even if you didn't know that, you'd figure out that it has to be. And I've drawn this one a bit shorter. Now the angles are still the same. I've just drawn dashed lines to represent the horizontal. Okay, keep in mind, vectors can be moved around. Okay, they do not have a position. And now I've drawn the 550 Newton force here as well. Okay, now just like in the first example, there's no resultant force here. This sign is not coming crashing down. Okay, just like the student hanging in the gym too. So these two tension forces must sum to be the opposite in direction of the force due to gravity. So these two, when added, must give you a vector with the same magnitude as 550, but opposite in direction. So I know that this is like 550 long, okay? Now the two tensions, I don't know what they are. I'm going to call this T1, and I'm going to call this T2. And the goal is to figure out what their magnitude is, which gives us the tension. So let's look at how we're going to do that next. Okay, so a few things I noticed. Obviously, this is a right-angled triangle here. If that's 15 degrees, then we must have a 75-degree angle right here. Okay, just like that. Now I can think about this one here. I know that these sum to 550. So let's use the triangle law, or it's kind of the parallelogram law. And let's think about taking this tension here and moving it over here. So it's over here instead. So when I do that, it looks like this over here. And now these are head to tail. And so I know that when I add T2 to T1, that the result of adding those together is this vector right here. Okay, I've tried to keep this parallel. I mean, I didn't know what this length was, but I do know that this has to be 550 long. Okay, and it's going to be the correct length so that these line up exactly as they do in the picture here. Okay, so it's kind of a weird question because I know the sum, I just don't know what the angles are. Pardon me, I just don't know what the magnitude of these two vectors is. So it's like I gave you the sum and you got to figure out what the magnitude of these vectors would be. I'd like to point out that we know what this angle here is. It is also going to have to be 10 degrees. And there's a lot of ways to figure out that this angle right here is 10 degrees. It's the same. One way is to imagine that you took this and you copied it so it is now over here as well. Do you see that the Z pattern that's formed here, these are parallel because they're the same vector. And there's a Z, so this is 10 degrees here. So its angle of depression is 10 degrees to the horizontal, and the angle of elevation, if you move it, is also 10 degrees. I think that's the simplest way to realize why this has to be 10 degrees. There are other ways to do it. I could have completed the parallelogram here. I could have with T1 and T2. Okay, you know that this is 80 degrees in here because that's 10. And then you've got 155 here, so you know that this has to be 25 since these two angles in the parallelogram would have to add to 180. So there's another way that you could figure out that that has to be 10. Okay, that makes this angle obviously 80. And we're good to go. We've got enough information now that we can solve this. Look at the triangle on the left. Okay, we can figure out, we've got all the angles, we've got one of the sides. We can use the sine law to come up with this question, the answer to this question, pardon me. So T1, the magnitude of T1 divided by the sine of it be 75 degrees must be equal to 550 divided by the sine of the opposite angles, 25 degrees. Okay, multiply both sides by 75, okay, and solve for T1, and you should get an answer of about 1257 newtons. So there's the answer for the magnitude of the tension in the wire on the right. How about the one on the left? It's the same idea. We use the sine law again. This time we are going to have to use 80, the angle opposite T2. So the magnitude of T2 divided by the sine of 80, again, is equal to 550 over the sine of 25. And if you figure that out, you should get about 1282 is what I have here. So sure enough, the tension in the wire on the right, on the left, yeah, called T2, the one on the left, is a little bit stronger than the one on the right. And there's the answer to that question. The tension questions give students a hard time. I think the real key is to realize the position, the picture that you see doesn't give you the lengths of the forces. It gives you the direction of the forces, but not the length. So you need to actually take your position diagram and turn it into a force diagram, which kind of wrecks this horizontal idea. Like, it's kind of nice to have this horizontal line, but this isn't the triangle here that we're working with. The triangle we're working with is this right here. Okay, this can also be done just by completing the parallelogram. It's the exact same kind of calculations. So in this next example, we have a 20 kilogram trunk resting on a ramp, and the ramp has an angle of elevation of 15 degrees. So we know that this is 15 degrees. That makes that 75 degrees as well. And we want to calculate the components of the force of gravity in the trunk that are parallel and perpendicular to the ramp. So you can take a force and break it down into whatever components you want. But in particular, in this example, we have the force of gravity, which could be broken down into the sum of two other forces. One force that's parallel to the ramp and another one that's perpendicular to the ramp. And those forces are important because the one parallel to the ramp is what causes the trunk to want to slide down the ramp, and the one that's perpendicular to the ramp is the force due to gravity that wants it to sit onto the ramp. So in this example, those two forces, which sum to the force of gravity, because we're breaking it down into its components, are very helpful for describing what happens in this situation. So, I mean, the first thing we need to do here is calculate what is the magnitude of the force of gravity, the length of this vector caused by a 20 kilogram trunk. So we get that just from, I'm going to call that FG, just from taking 20 kilograms, timesing it by 9.8 newtons per kilogram, which gives us that magnitude, which should be 196 newtons. And there we go. So again, I'm calling this F of G, force due to gravity. Okay, now the two other forces, one is acting perpendicular to the ramp, which looks like this, and the other is acting parallel to the ramp at a 90-degree angle, which would look like this. Okay, so since this is perpendicular to the ramp and parallel to the ramp, I need names for, I'm just going to call these X and, or Y and X for now. We'll just keep it really simple, vector X and vector Y. Okay, and they make a right angle with each other. And we need to calculate their magnitudes. Now, if this is 15 degrees, then right in here, I haven't left myself a lot of room, right in here is a 75-degree angle. And that means that there's another 15-degree angle in there. So this is just a right angle triangle we can solve. Remember, we know the hypotenuse of this right angle triangle is 196. So we can say that the cosine of 15 degrees will be equal to the magnitude of y divided by 196 newtons. And that should give us about, let's just say, about 189 newtons. And we also know that the sine of 15 degrees, that over here, sine of 15 degrees is going to be equal to the magnitude of x divided by 196 newtons. And when you figure that out, you should get the magnitude of x to be approximately, I've got 51 newtons. So those are the two forces. This force, the first one we calculated, that's what pushes it into the ramp. So the component of gravity pushing the box into the ramp. And the second, pushes into ramp. The second force is what makes it want to slide down the ramp. Only a 51 Newton force causing it to slide down the ramp. And we could keep going with this problem. We're not going to, but you could look further at it and say, well, depending on if it, say that you set this box up and it doesn't slide down the ramp. Well, what's stopping it from sliding down the ramp? Well, there's another force that must be the force of friction, which is 51 newtons in the direction up the ramp, and so on. So just this idea that we can take, especially a force due to gravity, and can break it up into different components. Another important application for vectors is velocity. So velocity is speed plus direction. And velocity is always relative to the ground, to moving water, to the air, to another object. For example, if I say that I'm, jogging 15 kilometers an hour, that's relative to the Earth because the Earth is moving at an incredible speed as well. If I'm traveling in a plane, there's a couple different velocities with the plane. There's the velocity relative to the ground, and there's the velocity relative to the air around you, and both matter. I mean, how long it takes you to get from Toronto to Calgary has to do with your velocity relative to the ground. But how fast the plane travels, based on the power it has, that has to do with the air around it. Same with on the water. If you have a boat that can go 80 kilometers an hour and there's a 10 kilometer an hour current, then your boat can actually go 90 kilometers an hour relative to the ground. Okay, because the speed of the boat, based on how strong the engine is, has to do with how fast it can go relative to the water, which is also moving. It's kind of like walking on a treadmill, same sort of idea. So let's take a look at an example with an airplane. So the directions here I'm giving you are kind of annoying because I'm trying to teach you the way that your textbook does directions, and even though I don't like it. You've got an airplane that's steering north 45 degrees west. So that means think about going north, then 45 degrees west. And here's what that looks like. So here's the vector that represents the plane's, not its final velocity, but its velocity relative to the air. And I'm going to call that V for velocity with a little subscript for A for velocity with respect to the air. So we know that that plane can travel about 500 kilometers an hour, or that's what it is traveling in any case. So that's 500, okay? So we can sort of pretend that this pilot, they didn't put any thought into where they're going. They just pointed north 45 degrees west, okay? And they went 500 kilometers an hour. Maybe that's as fast as the plane can go. But of course there's a wind, and wind makes a big difference when you're in a plane because it's the medium you're traveling in. So when it moves with you. Okay, you move with it, pardon me. So if your plane can only go 500 kilometers an hour and there's a 100 kilometer an hour wind behind you, guess what? Your plane can now go 600 kilometers an hour. This wind is coming, winds directions are often given with the direction that they come from. For example, a west wind actually is traveling east. The wind is coming from the west. This wind is coming from north 65 degrees east, N65E, which means think about going north and then a direction 65 degrees east. So this angle here is 65. I forgot to write the other one, which would be 45 degrees. Okay, and we'll use W for the wind vector. The wind vector has a magnitude of 120. Okay, so you can see from this picture already that this is a bit of a tailwind. It looks like this wind is probably going to help the plane a bit, assuming this is the direction it wants to go in. It's going to speed up the plane a bit, but it's also going to push it off course this way, okay, because the wind's coming from that way. As it turns out, the velocity, we're talking about the velocity of the plane relative to the air. We're interested in the velocity of the plane relative to the ground. So what ends up happening, I'll call that V of G, is you can take the velocity of the wind and add it to the plane's velocity. So the velocity of the plane in the air plus the wind equals the velocity of the plane to the ground. And look at this, they're already set up head to tail. Isn't that nice? Because now we can just complete this picture and we can say that there's our resultant velocity. That's the vector that represents the velocity of the plane relative to the ground. Okay, this looks like it's, there's 110 degrees. So it's just a matter of using the cosine law to determine the length of this vector. Let's do that. Okay, so we set it up with the cosine law, and sure enough, we have 500 squared plus 120 squared minus 2 times 500 times 120 times the cosine of 110, 45 plus 65, and we get 553 kilometers an hour, which seems like a reasonable speed. The 120 kilometer an hour wind sped us up by about 53 kilometers an hour. Now, important in this example is we would like to know the direction that you're going to travel. So how do we do that? Well, we need to figure this direction, this vector's direction out somehow. So let's just take a look here. We need this vector doesn't have its tail at the origin, which would be nice because then we could describe it with respect to north, east, south, west, but it's up here. Okay. But remember the little trick I showed you. We kind of know that this vector right here, we know that it's going to be like, it's going to go like this. Okay, there, I just drew it right there even for you. We also know that the angle it makes with V of A, okay, is the same tail to tail as it is head to head. So this angle right here is going to be the same as the angle up here. And that angle's inside the triangle and relatively easy to find out. So that's the angle I'm going to look for. And I know that that's going to be the same as this angle here. And since we know that's 45 degrees west to north, we'll know how much west of north the new vector is. I'm just going to get that out of the picture because it's going to be a little confusing with it there. So I'll call this alpha. Okay, and I'm going to figure out the angle when they're head to head because I know that's the same angle as when they're tail to tail. This is just a matter of using the sine law. We know, we've got 500 here. We've got the 553 we just figured out here. We've got the 120 from the wind speed. Okay, we've got more than enough. We've got more than enough to use the sine law. I can even use the cosine law to find alpha if you want. The sine of alpha divided by the angle, the side across from it would be 120 is equal to the sine of 110 divided by 553. Oops, sorry about that. 500 and okay, multiply both sides by 120, do the inverse sine, and you'll find you get 12 degrees. Okay, so what does that tell us? Well, it tells us that this angle up here is 12 degrees, which again is this, if you imagine this vector now over here, vectors don't have position, this is 12 degrees as well. Okay, so this plane goes 45 degrees plus another 12 degrees if you want to think of it off course. So we can say that the plane would go north followed by 57 degrees west, 12 plus 45. I think your book goes, uses this notation, north 57 degrees west. I'm not a big fan of that notation. I don't know why you wouldn't use a bearing, like 0 to 360 degrees. 0 is north, 180 south, and so on. But that's what the textbook does, and so I'm just trying to take advantage of that notation so that you can answer the questions of the book, which I know isn't the greatest reason for doing something, but there it is. Okay, bunch of questions for you guys to try on forces, velocity, that kind of stuff. Okay.